Let's go through LeetCode 2940. Find a building where Alice and Bob can meet. For this question, it gives us an integer array heights, which represents the heights of buildings. And also a two-dimensional array queries. And the query, for every query, the first one is the Alice seat, and the second one is the Bob seat initially. And they say that a person can move to the right building where the right height is greater than his current height, so that you can move to the right, which have the building which is taller. And for every query, we are trying to find the index of the leftmost building the two person can meet. If they cannot meet, and then return -1. For example, this kind of there is a query 2, 4, right? 2, 4, 8, and 2. You'll see this 8 on its right. There is no building greater than 8. Then they cannot meet. That means we return -1. And for these 2, 2, right? So that two persons initially they sit at the same position. We just return this kind of position. So what we're thinking about is that for every query, we get the left and the right, right? Actually, the person is not important. We just have the mean of the Q1 and Q0, and as the left, and the max as Q right, and the max of Q0 and Q1. And we'll say if left equals to right, return right. If the height of the left is smaller than height of the right, we also return right. Only when the height of the left greater or equal to right, we need to do the special handling. All right. So what we do is that we have then what we left to our query is, for example, we have left 1 and right 1, right? And possibly left 2 and possibly right 2, right? And we have maybe left 3, right? Left 3 and possibly right 3, right? So we only left those kind of queries which have the left height greater equal to the right height. So we need to handle this kind of scenarios, right? So what we're thinking about is that for this kind of query, we do offline handling, because to do the manipulation use the online, we need to have to use the segment tree. To do the offline handling, what we're thinking about is that we sort those queries by its right index, right? So we create a new collections sort by its right index. And also we iterate the heights array, right? So what we do is that we are going to use a stack, a monotonic stack, to have the heights, to handle the heights. What we do is that we, for example, we have n-1, right? We push the heights into a stack. So this is n-1, right? So if n-2 is smaller than n-1, we push this one into the stack. And if we have n-3, for example, greater than n-2, what we do is that we pop out n-2, right? And instead we push a minus 3, right? So in this case, we have a stack, possibly in a monotonic stack, which is we view here like increasing one, right? But when we do the calculation, when we do the write code, it may be decreasing, because this is the on the bottom of the stack, right? Bottom of the stack. So we view here it's like a increasing one, right? If we viewing from the top to the bottom, look like increasing one. So that means on its right, the shorter building, it's will not count those kind of buildings, right? So what we need is that we in this stack is that to this index I, right? On its in the stack on its left does not have buildings taller than this kind of building heights, right? So what we do is that we iterate the heights array from the right to left. For example, we look at this query, and then we try to see this kind of stack, right? We find for this query, this R3, we need to find its left 3, right? So what we need is that we look at search in this ontologic stack, the first index greater than the height of left 3, right? So in this case, we update it. This kind of queries result. On the same time, right? If we move here, right, this kind of height will pop out this, right? And we also add this to our stack, right? And also we binary search this kind of queries, right? So trying to see this left heights, the first one greater equal to this height. For example, we find this one, right? So then we update this. So doing like the monotonic stack and a binary search, the thing is that for our stack, right, we can use an array to simulate the stack. So if it is array, we can handle the index easily. Then do the binary search. That will be another advantages using array to simulate stack, right? We know Java stack, those kind of implementation not good, and so use array to simulate a stack. The another advantage is that we can easily to handle the index and also do the binary search. So after this kind of analysis, let's begin to write code. Okay. So we are going to have length, right? Int length equals to queries dot length. So we know the result will be equals new int length. So what we do is that we only create a list of int array, put those kind of queries which have the left heights greater equal to right into this kind of query list. Okay, we call QList equals new array list. So what we do is that for int I equals 0, I smaller than length I plus plus. So we know int left equals mass dot min queries I 0, right? And queries I 1, yeah. Into right equals max of max, right? So we know if left equals right, or height left is smaller than height right, right? We know result I equals right. Else to put that into our new list. Q list. Let's put it capital. Q list. Add. Because we want to handle the index, right? So and we want to sort by the right. So we need to have the index in it. So we do left, right, and the index. Okay. And now what we do is that we sort those kind of query list collections. Where is what's the problem? Did I print something wrong? New. So what we do is that we collections sort Q list by the right query, right? Let's have a reverse, reverse one, reverse. So we are going to have B1 in a A1, right? So now we need to from n-1 to 0 to do the to iterate the heights, right? We are going to create a monotonic stack. So let's have n equals its height, right? N equals height dot length. So we use array to simulate stack equals the new int. And we know we need to have an index equals -1, right? To simulate stack. So use array to simulate stack. It's kind of int. That's right. Int I equals n-1, right? I greater equal to 0. I minus. What we do is that while index greater equal to 0 and heights stack index smaller equal to heights I, right? In this case, we are going to have index minus, and otherwise we are going to have stack plus index equals I, right? In this case, we iterate from the n-1 to 0, right? Actually, in our stack, as it is, we maintain a monotonic decrease by the heights, right? Monotonic decrease, right? Monotonic decrease stack. So what we need to do is that we need to have a binary search for the query, right? So we'll say if the query if for this I, right, is just our query for the query right, we do a binary search for the monotonic stack, right? So we'll say if you list, right, it so we know this query let's also have an index called QID at the beginning equals with 0, okay? We know this one is sort for the second one in a reversible order, right? So if this one get QID 1, right, equals I, then we do a binary search, right? Binary search those kind of stack. We know so we have Q index plus, right? More one. So in this case, because it's possible the right can be overlap, so we'll have while, right? And also we'll have QID smaller than Q list dot size. Otherwise, it will be overflow, index overflow. So we binary search this stack, right? So we use a index array to simulate stack. We find another advantage here, right? So we write private int binary search. We'll have a height passing. We're going to have a stack passing, right? Stack because we put in a stack that is index. And let's have a start and let's have a target, right? So we'll see the search this index, right, will be our end index. That means that is the position in our stack, and start will be 0, right? So we'll say if end equals -1, that means this stack is empty, right? So we just return -1, okay? And we'll say while start +1 smaller than end. We'll have int mid equals start plus end minus start divided by 2, right? So we'll have if height stack mid. So this is a monotonic decrease array in our stack, right? So we want to find the last one greater than our target. So let's write, because it's a monotonic decrease. So we write find the last index in stack, which satisfies the height index greater than target. Okay. So let's see index. This index is a stack index. Okay. So we'll say if this height smaller than target, right? Then we are going to have end equals mid, right? So if it is equal, we also need to search on the end equals so we need to search on its left, right? So if it is equal, because we want to see the greater one, right? So that and also need to equals mid. Let's say else start equals mid, right? So we'll say if height stack and greater than, because we are search the last, so we are going to compare the end first, right? Return end, and we'll say if this one start, right? Then return start. If we didn't find, then we return -1, right? Then -1. Okay, so this is a binary search. So let's have, for example, int search index, right, equals binary search. Binary search height stack. 0 index, right? And the target is what? Is our height in our query list. Get QID, right? Get QID, the first one, right? That is so the thing is that if we didn't find any in this kind of stack, didn't find, right? That means we are going to return -1. So our result Q list get QID, right? This is the we have 2, right? Should have 2 equals SID. If it is -1, right? So we are going to have -1, right? Otherwise, we're going to have stack, SID. Stack is what in the stack is the index. In the end, we just return result, right?
Okay.
So doing the binary search, right? So this will be the query multiplied by log, right? Login. So the space will be max linear, right? The linear space.